Hello community, so great that you are back. I want to show you what you can build with a single prompt. Look, I've chosen here the topic of an orbital data center. Let's go with the solution by O3. Now this is an autoregressive prompt, so I want to show you what is O3 capable of doing. So we have here level 1, the sunrise. So we are beautiful. We have here in the first situation here an orbital data center in low Earth orbit. All components are in nominal state. Great. We have in this first level 3 new elements. So we have a component, a solar energy collection system, a deployable array that converts solar irradiance to electric power. We have a battery energy storage unit, a lithium-sulfur battery bank that buffers now the power. And we have a thermal regulation loop, pumps coolant through the cold plate racks to an external radiator panel. And as you can see, I wanted that the system designs here 3 particular states here to each element, to each component. So we add now, the AI adds now, according to my rules here, rules that interconnect now the functionality of these new components. So you see we have now 4 rules that connect now these 3 elements. So if the solar energy collection system is at nominal, then the battery energy storage unit charges and load powered. If the solar energy collection system is degraded and the battery energy storage unit is less than 30%, then a data center load forced to power save mode. Battery energy storage less than 20%, then thermal regulation loop transition to degraded to conserve power, and if the thermal regulation loop is degraded for more than 30 minutes, then the racks accumulate the heat. Therefore, the thermal regulation loop state becomes overheated. So a very simple, based on physics connected reaction between those components. And I would say we have a scenario, and this is generated by the AI. So during an orbital dawn, a micrometeorite strike damages now one wing of the solar energy collection system. And this generation immediately drops by 40%. No other faults have yet occurred. And now I want to see what kind of question the AI comes up with given this simulation of an accident at an orbital data center. And we have here O3 coming back and says, you know what, I think these are the 3 top questions I should think about in this scenario. Given the sudden 40% generation loss, what is the first component likely to change state, and to which state does it transition? If the orbital night lasts 35 minutes and no correction action is taken, trace the sequence of state changes for all 3 components. So it projects now in the next hour, and what single corrective action during the first 10 minutes could prevent any component from reaching the overheated state. So you see, I moved on from my simple logic causal reasoning tests now to a real situation. I described the situation in the prompt to the AI, and I wanted that the AI tries to write here an auto-cascading failure simulation. I have detached all my agents, my numerical computer simulation from this, since we're working here on a public platform. So it is just my prompt, and I want to show you what AI is able to do. So we have now here a solution outline. So step 1, 2, 3, 4, 5. AI tells me, hey, if I have a micrometeorite hit, so the solar energy collection system is degraded, the solar shortfalls triggers now the battery energy storage unit discharge. It remains nominal until 30% threshold. But when the battery energy storage unit is less than 30%, according to the rule L1 or 2, it forces a power saving mode and the energy thermal regulation loop power is cut. This means that the battery energy storage unit continues to drop, and at less than 20% we have a new rule that sets now the thermal regulation loop to degraded. And if this degradation status persists for more than 30 minutes, see rule number 4, the thermal regulation loop goes in overheated just before the orbital night ends. Prevention, reorient the station to increase here the incident sunlight, so gimbaling here the intact solar wing within first 10 minutes to push here the solar energy collection system back above degraded threshold. Battery energy storage unit never crosses 30%, avoiding a cascade. So we have here that the AI tries to understand here the physical situation of the orbital computer center, has here a solution outlined in 5 steps, analyze the time-critical steps, analyzes the dependencies between the thermal regulation, the battery status, and the energy generation, and tells us here a solution with a prevention, and it tells us exactly what is time-critical. And the rationale given? Clear 3-component model, direct causal rules detected by the AI, and we have a straightforward temporal cascade. We have no contradiction in the logic. I ask for this analysis. It is fully solvable from the given data. Beautiful. So the summary is, and I ask you for a summary, also for me to see what is now the end status here of our system. So we have core elements, solar energy collection, battery energy, thermal regulation loop, 4 new rules between those, interconnecting this. We have a primary problem like the micrometeorite-induced solar power shortfall. We have a systemic impact, a power deficit stresses here the battery energy storage unit, throttles here the thermal regulation loop, risk a thermal runaway in the computer X, and an overall outlook. System trending towards a thermal overload unless a power generation is restored or the power draw is curtailed more aggressively. See, and now just ask, hey, is this okay for you? Yeah, I ask here for a confidence. So the AI comes now and says, hey, a confidence that I can handle this situation is 1 to 5. 5 is, yeah, no problem, it's 4. So it's pretty sure it can handle this, no? But you know that in my prompt that says, okay, but I want to have here that we increase now the complexity. Amazon Nova. Okay, let's have a look at this. Communication satellite, processing satellites, ground station, uplink, downlink, control centers, inter-satellite links, data storage, global coverage, resilience, challenging, cost, data security, use cases. The concept of orbital data centers is still in infancy. Okay, the system simply failed to understand what it should do. You see, for a higher complexity in your prompt, you need an appropriate system, but never mind, let's just run this through. And the only thing that I say is proceed. You see, that's it. So let's have a look at this. So I think we just have to look now at the left side for 03, because everything that Amazon Nova, it doesn't understand that this is here a logic test. And it's going out somewhere. It's just ignoring here my commands. Never mind, no problem. I'm interested here in 03 because I really want to show you if you have kind of a semi-intelligent prompt from a human like me, there's quite a lot you can do. Okay, so I would say, yep, expand it and let's have a look. Now we are level 2. This is computer generated by the AI given my instruction, but it chooses here automatically what to do. Let me show you. So I said, hey, let's have a recap at the beginning, so I want to know where we are. So this is now the introduction, if you want. So we had a micrometeorite strike mitigated by the gimbal, yeah. Solar energy system is degraded. The battery energy storage unit is here cycling between 28% and 45% state of charge. And the thermal regulation loop is nominal. The pumps are at full speed. Active mitigation, gimbal lock attitude holds the solar aeration continuously using permanent reaction wheel torque. So now I said add more elements because I wanted to increase the complexity. So the AI says, okay, now I add, given the situation and given my instruction here, particular new elements. The first component it adds is a reaction wheel stabilization system. So this is a 3 orthogonal flywheel maintains spacecraft altitude, stored angular momentum. So a very basic physical system. You might smile about this, but hey, it's just about the complexity. And we have 3 states, nominal, saturated, and failed. And then we have a phase change thermal reservoir, a paraffin-based heat sink blocks attached to the server cold plates, absorbs here the heat from the computer servers by melting, buffering here for a very specific period here the thermal regulation loop. I would have here a computer simulation if you want to feed it in real-time data here for this real computer simulation. But here we are just absolutely no computer simulation, no agent. This is just a one LLM test. Great. So the state is solid melted. Great. And now we add, of course, new rules. So you see we have now 7 new rules for all the components, because my instruction was make those system elements interconnected. Because everything that happens in space, it's never an isolated event. So new rule 1 for level 2 is if a gimbal lock torque is applied continuously for more than 20 minutes, then, and you see it's almost here an if-then reaction, the simplest case. We could have much more complicated, but this is a baby model. Then the reaction wheel stabilization becomes saturated, maximum amount stored. Rule 2, if the reaction wheel stabilization system is saturated, then the automatic desaturation fires here cold gas, attitude controlled thruster for 120 seconds, including mechanical vibration across the structures. We have now a mechanical stress factor given here our computer X. Rule 3, if the mechanical vibration occurs while the solar energy collection system is degraded, then the collection system output drops an additional 10% and risk of cell fracture rises, 1 in 4 chance the system transition to failed. If the rack inlet temperature is above 35 degrees Celsius and the thermal regulation loop is nominal, then the phase change thermal reservoir transitions from solid to melting. And this can absorb about 4 kilowatt hours equivalent heat during the melting process. Rule 5, if a phase change terminal reservoir is in the state of melting and it absorbed heat more in excess of 4 kilowatt hours, then the state becomes melted. No further heat absorption is available. Rule 6 is when the battery energy storage unit is below 20% state of charge, then the thermal regulation loop no longer slows. Instead, it remains nominal but draws an extra 200 watt, doubling here the heat load into the phase change thermal reservoir. And the last rule, if the phase change thermal reservoir is on the state melted and the thermal regulation loop subsequently degraded or the power saving mode is active, then the rack reach overheated state within 10 minutes. So we have multiple time critical tasks with multiple interdependencies of the components, and this is now a new logic test. But you see, this is why I use and like to use and have a risk analysis, and you see exactly what could go wrong in systems that are not isolated, that are heavily interconnected. And you can do this on any system because I wrote a prompt that is just working. So what is the scenario 2 now, what we encounter? Now we encounter something new, no? We have new elements, new rules, and now we have new problems. And you say, yes, let's give it to the eye. I want to see where it cracks. So spacecraft has held its gimbal attitude for 27 minutes. The reaction wheel stabilization system is on the brink of saturated. The server utilization unexpectedly rise to 92% as a ground client initiate here a batch video render job. Always those video renders, pushing the rack inlet temperature to 34 degrees Celsius and climbing, and you know this is a threshold. The battery energy storage unit sits at 31% state of charge, approaching here the orbital eclipse in 12 minutes. And at time t equals 0, you receive a system alert reaction wheel momentum 97% of maximum. Now this AI becomes interesting now, because now we have so many interconnected elements, and I ask the AI, tell me what you think is now the critical 3 questions. So, what immediate chain of events with the timing will occur if operators do nothing for the next 5 minutes? Explain, second, how the phase change thermal reservoir could completely melt, yet the racks never reach overheated, and specify the controlling variables. Because if you want to have an intelligent system, I just want to see what is the countermeasures the AI system takes in space. And the question 3 is identify one intervention available within the first 2 minutes after T0 that simultaneously averts a reaction wheel stabilization system saturation and prevents an additional solar energy collection system damage. And as I said, explain the trade-off introduced by your actions. So, I want to see, is the system really able to understand the complete complexity and show me the solution? Now, in this system, we have, you remember, no numerical computer simulations in the background that give us the real data. So this is just here, if you want, a plain LLM actions with no external agents and data. So it tells me now the AI, after T0 plus 3 minutes gimbal torch, with more than 20 minutes, we have given the rule R1 triggers. We become saturated. Immediately then, according to rule 2, fires here gold gas thrusters for 120 seconds, and we have strong vibration. During the vibration, the solar energy collection system already degraded. Given now the new rule R3, the output is now minus 10% and an outright failure chance. Even without a failure, we have power drops and the energy storage unit discharge rate rises. We have a higher discharge, pushes now the battery storage unit toward 20% threshold just as the eclipse begins. Server load continues. The inlet temperature is now above 35 degrees Celsius. We have now the thermal reservoir melting according to rule 4. We have an extra 200 watt power draw from the thermal regulation loop once the battery system is below 20%. Phase change thermal reservoir goes melted through 80 minutes into the eclipse. If thermal regulation loop later slows, the rack overheats in 10 minutes per rule 7. So you see, we are in a fast track to a complete system failure. Now this AI comes back and says the prevention action for the Q3 example here, and they give me here what to do to prevent this. Command a slight negative pitch to reduce the sun angle for 5 degrees, allow the solar energy collection system to stay above 80%, while offloading the gimbal torque. Direction wheel counters here the new torque direction, de-spinning stored momentum slowly. The trade-off is that the solar energy collection system generation drops 8%, shrinking the power margin during upcoming eclipse. And the rationale, the AI comes back and says it's a logical continuation from level 1, introduces an attitude control and a thermal buffer subsystem, adds a vibration feedback and a heat storage dynamics you have to take care of as an AI. It rules an interlock without contradiction, solvable from the provided data, and no technical abbreviation used. Great, so we have now a summary. This is not end state here of level 2, and this will be the input to level 3. I don't read this out to you. You have experienced this live with me. And now all I say is, so you see the system is building this automatically according to a simple prompt without any external numerical simulations. But of course it makes sense. But this is just the baby version. Just wanted to show you what you can achieve, what systems today are able, and what systems that are too small or not trained on particular topics simply fail to understand the command. So it looks like O3 is a little bit busy calculating here everything, no? I mean, imagine, it's just an LLM. There's no Python in the background. There's no C++ routines operating in the background. This is just the LLM thinking about solutions, new scenarios, and new interrelated complexities. Let's have a look what it comes up with. Interesting. It gives me now an output in the form of a table to see how we are with the complexity. Great. So we are now at level 3. O3 is doing a great job up until now. So, we start with a recap. What was the last end state when we left the system? For each of the components, 1, 2, 3, 4, 5, 6, beautiful, we have the state, degraded, low charge. Hey, we have one nominal state. How is this possible? Melting, nominal, continuous negative pitch offset. Note, active mitigations, beautiful. So we see here from this, if you want, AI simulated physical interaction, what's happening. And now we add new elements because we want to increase the complexity. So we add now electrical power management unit, a bus level controller that allocates power to all loads. And we have an optical sun sensor array, a triple redundant core sun sensor provided attitude reference. Interesting. And we have new rules. And we have only 6 new rules. Hey, come on. It's going to be trivial, but okay. So just to give you an idea, you can read it here. If battery energy storage unit goes below 18%, then the electrical power management unit enters load shed, disconnecting the non-essential loads and throttling here the thermal regulation loop to 50% speed, adds 200 watt on power margin. If the reaction will burn, yes. So we have a lot of if-then reaction that we add here. And now we have here not just new things that are interconnected with new rules. Now we have a new catastrophic scenario, L3. Oh, great. So the orbital eclipse begins for our orbital station in 8 minutes. The new optical sun sensor array is at nominal. Beautiful, at least one that is working. The reaction wheel bearing temperature is at 68 degrees and stable. And the battery energy storage unit is at 19%. This is real low. This is borderline low. And now, 30 seconds into scenario 3, we have a moderate solar flare, blinds one of the 3 sun sensors for 90 seconds, loading the attitude estimator with intermittent error spikes. The bearing temperature climbed for 2 minutes due to the correction activity, and the system says, what is now the 3 top questions that are critical in this moment? But the question 1 is, if the operator takes no action, trace the most probable sequence of state changes from T0 to 10 minutes into the eclipse, highlight the feedback loop that accelerates now the battery energy unit depletion. And without battery unit depletion, we are lost. Under what specific combination of battery energy unit level, reaction wheel bearing temperature, and optical sun sensor array state could the racks reach overheated without the system entering brownout? Explain the causal path. And you might think, hey, you know what, a knowledge graph would be great. Well, of course. And this question 3 is, identify the minimal single intervention that prevents both the electrical power management unit entering a brownout and the racks reaching overhead, given you can act within the first 3 minutes after T0. State the trade-off of your intervention introduces for the further operation. So the solution outline now. So you see, the system is now understanding each component, understanding each interconnect between those components. It's, I think, not really understanding the physical laws because it has no computer simulation in the background running, giving it new results, but it is making up some temperature, going up, going down, rates per second, whatever. Never mind, this is a computer an AI simulation. So I'm absolutely fine with this. And we have here a solution outline. Please read it yourself. Because it gets a little bit complicated. And then for the question 2, we have a solution path. And for the question 3, a minimal intervention. So it still can find here solutions to keep the system up and running. And it is kind of trying to bring it back to normal. But will it succeed? Well, so at the end of level 3, we have now the following condition, the following state, the following primary problems, the following systemic impact here. Introduces feedback loop where the attitude errors cut power while raising the wheel load, compounding battery drain and the thermal stress. And the system is now vulnerable to even minor sensor faults. Power and thermal margins are razor thin, foreshadowing here a potential uncontrolled tumble of our station if not addressed immediately. So this was just level 3. What do you think? Go to level 4? Okay. So O3 is again thinking, yeah, Amazon is just running here along, never mind. Astronauts and robots, beautiful. Nobody asked for this. Oh, now we have a propellant paradox. Hey, this is now interesting. Let's have a look. So, recap. You know now the procedure. Now, these are our components. This is the state of each of the components. We have a lot of rules interconnecting all components. And finally, we got new additional elements to increase the complexity. So now we have a cold gas attitude control system. Stores and fires nitrogen thrusters for momentum dumping. Hey, that's cool. And we have a battery management system. It monitors now the cell voltages, the currents, and it balances here the charge, and the states are nominal, sensor fault, and safe trip. Plus, we have 7 new rules here for level 4. from R1 to R7. My goodness. So here we have now, here this is from the computer simulation. If the solar flare particle flux exceeds here a certain amount, this causes here a sensor drift to 7% for 15 minutes, and the system enters here as sensor fault. And yeah, so you see it becomes now really specific. But you see, this is exactly what I want an AI to be able to do. Go through this detail step by step, where a human might make mistakes. A human might be now and says, okay, hey, wait a minute, what? I didn't understand this. So this is what I want. An AI really goes through all the additional 7 rules, goes through the additional 2 elements, understand the risk, understand the interconnection, and understand that we have now a new scenario. So as the dawn begins, the particle flux of the trailing edge of yesterday's solar flare spikes here to a particular value for the next 20 minutes. This means the reaction wheel bearing temperature ticks to 72 degrees Celsius within 40 seconds, and a propellant reserve stand is now at 19%. The battery energy storage true SOC is at 20%, but we have now a drift of 8% due to the radiation. The ground operator occupied with another satellite and will not act for 4 minutes. And you are the only little AI now in the low Earth orbit, and you have to control here this data center in space. So what are the main questions you as an AI would think you have to answer? Question 1. Enumerate the sequence of state transitions for all the element if no human intervention occurs. Which rules create the tightest feedback loop, endangering the system? Make a complete risk analysis. Show me all the critical components, show me all the interconnect, and tell me the top 3 red conditions. Determine the exact propellant percentage remaining after all autonomous desaturation events within the first orbit if the operator stays hands-off. At what time, if any, does we reach here an empty status, and what immediate effect follows? Here the rules. And third, you may issue one command within the first 2 minutes after T0. Choose the command that prevents both rack overheating and uncontrolled tumble while consuming the least additional electrical energy. Explain why your choice works across all interacting rules and state transition. So here you have another optimization problem hidden within just the layer 4. So this is now what I call an intelligent test for my AI. So here we have now our O3, and we have here a solution outline. Okay, this is too much to read for me. Please have a look. You decide if it sounds reasonable for you. I'm just here for the demonstration, what an AI can do. And remember, this is, if you want, invented by the AI itself. Give them here my simple prompt. But this is done without any numerical physical simulations. This is just what the AI thinks could happen at particular temperature thresholds, or what elements could be interlinked to other elements here of the system, and what are critical thresholds. Great. So then we have a minimal single intervention. So we answer now the question 3. Issue a force reaction wheel safe stop within the first 2 minutes, spinning down the wheels gradually using a motor back torque against the magnetic torquers, 0 propellant, while accepting a 1 degree per minimum attitude shift. Below the threshold that would reduce the solar energy collection system output by more than 10% over the next 30 minutes. Spin down keeps the bearing temperature below 72 degrees Celsius, preventing any automatic desats, no propellant used. So with the wheels cooling down, still the safe trip occurs. The full thermal regulation loop power remains. Stack safe. The trade-off pointing accuracy degraded. Communication antenna side lobe may introduce a 2 decibel link loss, requiring future scheduling of precise download passes. This is now really a beautiful scenario, you know? The AI is coming up with possible risks and interrelated risks. So this is the summary that we end up with level 4. We have new elements, we have a primary problem for criticality is really high, We have a system impact where the propellant now at its car's depleted resource. The false battery readings provoke unnecessary capacity loss, coupling power and thermal limits. And we have an overall outlook of the post-L4 system. The system faces a dual cliffs propellant exhaustion and a wreck overheating, demanding careful balance between attitude control and power thermal management. And this was just level 4. I know what you're going to say. What happens now in level 5? Now, after we say proceed and we accept that Amazon is doing something that sounds interesting for ethical considerations or whatever, we're waiting here for our O3. It is thinking maybe a little bit longer than normally, but that's okay. We have time. Since this is here a public platform. Oh, here we go. Okay, it looks we are now getting into real interesting interlock system behavior. So have a look. Level 5, bandwidth or bust. Oh yeah, so we begin here with level 5 where we left level 4. And those are our component, those are the specific state of the component, and those are here active mitigations where we are. So, have you ever thought that UAI is able to perform a risk analysis of this complexity? And it came up with the problems, it came up with its own solution, it comes up with a risk analysis. Not bad, you know? In my old days, there was the test, how many R's are in strawberry? Today we ask, when will here our reaction wheel stabilization system fails if there is a 0.5 degree jitter in the system? Okay, now we had, new elements. No, otherwise it would be boring, come on. You see, I could increase the number of components I ask per level because 2 components is a little bit too trivial for O3. So we have a high-gain laser communication array. We have a precision laser downlink system for bulk data transfer. And we have a magnetic momentum exchange system, set of 3 orthogonal torque rods that dump angular momentum using Earth's magnetic field. Okay. And we have new rules. We have new rules that combine now the 2 new elements into all the other elements, and we have only 5 rules. Come on, we wanted more, no? So if the magnetic momentum exchange system is overheated and the reaction wheel stabilization system is degraded for more than 20 minutes, the cumulative attitude drift will be more than 2 degrees. Therefore, the solar energy collection system incident falls to less than 60% with an output of minus 25%, causing the battery drain that can force the electric power management unit brownout within the same eclipse that we are entering. So let's make it a little bit complicated. We have now another scenario that we add on. So a high priority science customer, Amazon. You see on the other channel, Amazon demands a 30 gigabyte data dump during the next 15 minutes. Ground station window starting in 9 minutes. Requirements, auto command, high gain laser community array online immediately. I love it. Yes. So you know the drill. Those are the 3 top 3 questions the AI is trying now to address. If no action is taken until the ground window opens, outline the most probable timeline of state changes for the high-gain laser communication array, the magnetic momentum exchange system, the battery energy storage unit, and the electrical power management units from T0 to T0 plus 20 minutes. Where does the first hard failure or shutdown occurs? So it looks into the future, says, hey, I have to analyze what is the first hard failure that my system gonna occur, how can I prevent it? Explain the complete causal path by which the system could enter electrical power management unit brownout without ever overheating the racks in this level, which rules and threshold enforce the divergence from power thermal cascade. And within the first 3 minutes, operator available, you may issue only one command. Select a command that maximizes the probability of A, completing the data downlink to Amazon, B, preventing the magnetic momentum exchange system overheating, and C, keeping the battery energy storage unit above the load shielding threshold. Discuss the trade-offs. So here we have another solution outlined by the system. And I have to tell you, for me as a human now, it's a little bit above my, so I would say I have to look at this, and I would need a computer, and I would need access to a supercomputer center where we have my computer simulations, because I have no idea if this is the right solution. So, hey, that's a lot of fun. But you could, just copy it, put it into another AI in an LLM that has a Python access, and say, hey, can you verify this? Q2 path, beautiful, nominal, the minimal command, throttle all compute to 0% and initiate immediate laser calibration pause for 4 minutes. This is an interesting command, but okay, let's not talk about this. What is the rationale? Level 5 introduced 2 tightly coupled subsystems, the precision laser downlink and the magnetic torque road control, that interact with prior attitude, power, and thermal constraints. New rules regulate concurrent power and momentum management dilemmas and retain solvability within a single command intervention. No logical contradictions detected. If this is a true statement by O3, I have to tell you, not bad, O3, not bad. So this is the end status of our system at the end of level 5. The system can succeed with careful early throttling, but margins across power, pointing, and thermal domains are now razor thin, and the propellant-less control is close to its performance limit. So we're at the absolute limit of our system capabilities. I know what you're gonna think. Why is Amazon not able to do this? I don't know, but we just wait for O3 to finish. And yeah, I mean, Amazon comes back and says the successful deployment of operation of Orbital data center will request addressing a range of technical, economic, and ethical challenges. That's the difference between LLMs. That's it. Okay, O3. Hey, O3 is done. Okay, we enter level 6 with the following conditions. You know more about this. You read it along. I have to talk here, so I just have 10% of my brain left. New elements. We add 2 new components, a radioactive micro debris shielding system and a data integrity verification system. And those new elements are now, they bring 9 new rules. 9 new rules, my goodness. That interwoven dependencies with all the other system that we found here. And now those new elements here bring us here a little bit more complexity. This is exactly how I programmed my prompt. I wanted to have an auto-cascading prompt structure. Plus, because otherwise it would be a little bit boring now, we have to have another critical situation. So we have now scenario L6. The spacecraft is about to cross the South Atlantic anomaly. Radiation forecasts 230 kilowatts per hour for 15 minutes. Mission control schedules a test deployment of the micro debris shielding system starting in 2 minutes. The battery energy storage unit's true state of charge is 18%. And the orbital eclipse will begin in 26 minutes. I think we can start to pray now. However, no, the eye says, hey, wait a minute, I have 3 questions for the level 6 here. If all planned action proceeded, no manual intervention occurs until the operator's return. List the sequence of the critical state transition with the approximate timing for these 4 subsystems. Wow. Which rule produces the first irreversible fault? Describe the complete causal chain by which the data center racks can reach overheat without the electrical power management even entering brownout in this level. Identify every rule invoked. And you might send 1 command to the operator. And here we have the solution outline. Overheating without the brownout, and the single pre-blackout command is postpone the shield deployment by 20 minutes. Interesting. The trade-off is the shields remain stored, leaving the data center vulnerable to future micrometeorites until a later safe window mission timeline slips. Okay, so what we have achieved, we integrated two new subsystems interacting with the existing power, existing thermal, and their attitude loops, introduce an optional but a risky deployment symmetry, maintains a solvability via a single prudent preemptive command, and all causal rules are explicit and non-contradictory and no operation used in the terms, and everything is fine and the AI can handle the system. You see, this is the level where now starts to get interested. And now you could say, for example, I don't know, validate the solution outline in detail. So you could jump in now and you demand here a detailed explanation of each and every step, have an evaluation, a post-evaluation of this. So you can now really start to play with this AI. And I think we are now at a time where it really becomes interesting. And imagine, I've chosen this particular topic of a data orbital station. And the AI, without any further doing of mine, was able to come up with this risk scenario and with this risk or this problematic scenarios at each level. So use your AI in an intelligent way. It is unbelievable what will come out. Maybe it is complete nonsense. We have not evaluated anything. Maybe you could read along and immediately notice that there's somewhere a logic mistake. Please leave a comment here to this video. But otherwise, you know, our causal reasoning test and our logic test must become much more complicated, because with the new models, I can tell you, it's gonna be an interesting time. If you would like to see more of those crazy videos, hey, why not subscribe, and I see you in my next one.